All right, in this video, we're going to be focusing on graphing exponential equations. So we just looked at what an exponential equation is, and now we're going to look at graphing and what it looks like graphically. I showed it a little bit with the ball bouncing, the golf ball bouncing, but I want to really delve into it here. Before we talk about graphing exponential equations and what that form looks like, I want to refer you back to graphing quadratic equations. Now, you do not need to write this down. You've already written it down. I just want to refresh your memory. So this was our vertex form for graphing a quadratic equation. When you had this quadratic equation, the plus k here at the end gave us our vertical shift, up or down. The plus h within the parentheses here with the squared gave us the horizontal shift. And remember, it was the opposite of what you would think. If it was x plus h, you went to the left. If it was x minus h, you went to the right. And so it's the opposite of the way you might think. And then the scale factor out front, told us how much that parabola was going to stretch vertically, if it was bigger than 1, or compress and kind of flatten out vertically if it was between 0 and if it was a fraction. If it was less than 0, it reflected it over the x-axis, and made it into kind of an N shape. So now, watch closely, because we're going to go back to exponential. Here we go. Wow, almost the exact same. So go ahead, pause it, write this down, and then I'll go through it. I'm assuming you paused it. It's very, very, very similar to the vertex form, not vector, vertex form of graphing a quadratic. It looks practically identical, but I'll go through it again. The exponential equation, then, we've got some base to some power. We can multiply a scale factor out front plus some number if we want. So this was that exponential form. The plus k at the end here is still the vertical shift. Still works the same way. Plus k moves it up, minus k moves it down. The x plus h here within the parentheses. Now this is where the x is in the exponent. The domain is in the exponent, so it's no longer squared. It's not a quadratic, but in this exponential form, x plus h gives us our horizontal shift. Just like before, plus h moves it to the left, minus h moves it to the right. The scale factor out front, if we multiply by some number bigger than 1, it's going to stretch it vertically and make it kind of it's almost like an L shape, make it a steeper L. If it's between 0 and 1, it's going to compress it vertically. It's going to make it a flatter L. And if it's less than 0, it's going to reflect it across the x-axis. There's one thing that's not on this list that is a little bit different with exponential functions than quadratics, and I'll show you what that is here in just a minute. So that's walking you through that. Let's look at some examples. So I'm going to delete this so I can just have it. There it is. So here are a bunch of examples, and I'm going to walk through these examples slowly. So if we have a graph, on the left-hand side here, you'll see a whole bunch of different examples that I'm going to walk through. So y equals 2 to the x power. This is my basic one that I'm going to use. So the base is 2 to the x power. Looks like this. There's your basic exponential function. When x is 0, 2 to the 0 power, anything to the 0 power is 1, and so the y-intercept is 1. There is no x-intercept because we have a horizontal asymptote here. Otherwise, it just keeps on growing exponentially. There's actually no vertical asymptote either. Even though it looks like it kind of goes straight up and down, it will go on forever. You can pick any big number of x and work it out. Okay, let's look at that vertical shift up and down. So right here, I've got 2 to the x plus 4 and 2 to the x minus 3. If you add 4 to the end, you can see with this blue line here, it takes the exact same shape, and it just moves it up 1, 2, 3, 4. So instead of the y-intercept being at 1, it's at 4. So it just moved everything up 4. Right here at x is 1, y is 2. 2 to the 1 power is 2. Moved it up 4. 1, 2, 3, 4. So all the points just shifted up 4. Same thing if you subtract 3. it moves down 3. 1, 2, 3. Every point on the line moves down 1, 2, 3. So it's the exact same shape, exact same graph, just shifted down 3. If we look at the horizontal shift, so we'll look at the next two here. On the left, x plus 4 in parentheses, so x plus 4 is in the exponent, x minus 3 is in the exponent here. So x plus 4 should move that graph to the left 4. So not plus 4 to the right, plus 4 to the left, which is the opposite of what we would think. And so there's this orange line. So this is my original line. I go 1, 2, 3, 4 to the left. Every point on that line is going to move 1, 2, 3, 4 to the left. Same shape, just moved over 4. Same thing if we go to that purple line, so minus 3, it's going to move it to the right 3. So every point on the line, 1, 2, 3, moves it 3 to the right. 1, 2, 3. Same shape though. All right, so that is similar. Scale factor. Let's look at scale factor. So here's my original function. If I multiply it times 4, because 4 is bigger than 1, it should compress it vertically. And let's see what that looks like. It looks like this. It almost looks like it's been shifted up, but you'll notice that we still have this horizontal asymptote at 0. With the plus 4 here, the horizontal asymptote became at 4. 1, 2, 3, 4, because again, it moved up 4. So the times 4 is going to move the horizontal, the y-intercept times 4. So 1 times 4 is 4. 1, 2, 3, 4. There it is at 4. 0, 1, 2, 3, 4. Every point is being multiplied by 4. So if it was at the point 1, 2, 2 times 4 is 8. So 5, 6, 7, 8. Yep, there it is. It goes at that point 8. So every point is multiplied by 4. If it was at a half, now it's at 2. 2 times, or a half times 4 is 2, and so on. And so every point is being multiplied by 4. If it's a third, the same color, but that's all right. If it's a third, every point is a third as big. So it almost looks like it's being shifted to the right, but this point here does not move over. So at 1 here, it should just move over. If it was moving to the right or to the left, it's not. It's some fraction. And so it's being shifted. It's being scaled down. It's being scaled to a flatter point. 1 goes to a third, 2 goes to 2/3. Here we have 4 goes to 4/3, 1 1/3, and so on. And so every point is being multiplied to a third of its original size. All right, so that's scale factor. And then I guess one other thing that's the same as the quadratic, flipping or reflecting it across the x-axis. If it's a negative scale factor or a negative number out front, we're going to flip that over. And so we can reflect it across the x-axis. So that, again, all that is very similar to the quadratic. So if you were comfortable with the vertex form of the quadratic, this is going to feel very similar, very familiar. One place where it gets different is that not only can we reflect this function across the x-axis, we can reflect this function across the y-axis. Now, before I talk about that, let me show you why that didn't work with the quadratic. If you had x, I don't know, we'll go with minus 2 squared, like that. Reflecting this, actually, no, let's not even do that. Let's just do x squared. Reflecting this across the y-axis, if you flip it, if you take every point on this side of the y-axis and put it on this side, and take every point on this side of the y-axis and put it on this side, you're really not changing it. We have this line of symmetry vertically. And so when you reflect it vertically, it's the same exact shape. Reflecting it horizontally on the x-axis flips it down. But if you reflect it on the x-axis vertically, it's the exact same thing. It doesn't really change it. And so that just wasn't an issue with the parabola. With the exponential function, though, we have really two ways of reflecting it across the y-axis. One way is to make the base a fraction. 1 over 2 gives us this. You'll notice it almost makes kind of a parabola, except this is more of a V here. So it's not quite a parabola, but it reflects it across the y-axis. Reflecting across the x-axis gives us this blue line. Reflecting across the y-axis gives us this green line. So a fraction as a base will do this. I'm going to refer you back here. Well, no, before I do that. No, yeah, I will. Refer you back here to an earlier lesson when we had the golf ball being dropped. It was 2/3 times 2/3 times 2/3. So the base was a fraction of 2/3. And you'll see we have a decaying exponential function here. It's going down. And so we see that with our graph here. Another way to do the exact same thing is to make the exponent negative. 2 to the negative x, if you watch carefully, nothing changed, just the color. These two are exactly the same thing. It's because that negative exponent is going to give us a fraction. It'd be 1 over 2 to the x. And so it's the exact same thing because of that negative exponent. And we see that in this equation here. I kind of mentioned it at one point, but with this half-life, again, 1/2, half-life, we have this 2 to the negative t. That negative exponent really is the exact same as saying it's 1/2. The reason I use the negative here is because that's how it shows up in the text. And I wanted to be consistent. But that negative exponent is the exact same as if you made this base of 2 into a 1/2. And so you could have just as easily written this equation here as 100 times 1/2, and then a positive 7.2 over 2.4, because really that's what's going on. It's 1/2 every time. So it's a half times a half times a half over and over again. But that's where they're getting that negative from. Why they chose negative over the fraction, I don't know. But that's where that negative is coming from, is because it's the exact same thing as doing a half as your base. Either one is correct, and either one will give you the same result. Okay, so the big thing you need to have from this video, from this lesson, is this basic form of graphing. You're going to be asked to identify. You're going to be asked to identify which one is it. So it's going to be a lot of matching. Which equation matches with which graph. I'm not going to be asking you to physically create one of these graphs, but you are going to be asked to identify which equation matches with which graph. So knowing how the vertical shift works, the horizontal shift, and that scale factor, flipping it vertically and flipping it horizontally is going to be part of the quizzes, assignments, and tests. So there you go. That was graphing, and you can move on to the number E.